SwayamPrabha. Digital India. Educated India.
Hello everyone, welcome to lecture 17, and today we are going to discuss linear momentum balance in cylindrical coordinate system. You will see that in the next several lectures we will be working with cylindrical body, where using cylindrical coordinate system makes things easier. Therefore, it is important to derive the equations in this coordinate system. You remember earlier we derived the equations in Cartesian coordinate system x, y, z, but now we would like to derive it in r, theta, z coordinate system, cylindrical coordinate system. Okay? Because as I told you, the bodies, there are several bodies that we will encounter will be of cylindrical in nature. Okay? All right. So, let us start with the cylindrical coordinate system. So, here we have a z axis usually, and suppose we have a generalized cylinder. Okay. So, this is called a generalized cylinder, and it is generalized because the radius of the cylinder is changing over the axis of the cylinder. If the radius is fixed, it is a simple cylinder, otherwise it becomes a generalized cylinder. Okay. So, maybe we will have an origin here in this plane at z equal to 0. So, this is z equal to 0 plane, all right, and this axis is the z axis. So, any point will have coordinate small r, small theta, z, and if you project this point on the z equal to 0 plane. So, when you project it down, it goes somewhere, and this point will then have only small r and theta, and z will be equal to 0, is not it? And if we just draw that projected plane here, suppose I look at this z equal to 0 plane. So, any point, the projected point has coordinate little r, little theta, and there will be a baseline here. So, when we join this projected coordinate from the center O, then this line will make an angle theta from the baseline, and the length of this line would be small r, is not it? And what are the directions? The directions would be, there is one E r radially outward, right, and another is E theta in the direction of increasing theta. So, when you increase theta, the direction that you get is this. So, that is your E theta. So, we have E r, E theta, and E z, which is coming out of the plane, right. So, the basis for cylindrical coordinate system is E r, E theta, and E z. They are the basis vectors. Remember, in Cartesian coordinate system, the basis vectors are E1, E2, E3, and they are fixed. But you see here in the cylindrical coordinate system, the basis vectors are not fixed. It changes from point to point. For example, you think of a point over here, and you join this line, then the E r and E theta associated with this point is different. So, E r is always radially outward. So, that is your E r, and E theta again in the direction of increasing theta. So, you see that E r and E theta for the 2 points are not the same, but E z is always the same. So, I can write here that E r and E theta changes from point to point, whereas E z remains fixed. Okay. Also, you have to see E r and E theta only change when the theta coordinate changes. If you only change the radial coordinate, then E r and E theta do not change. For example, you see here, let me draw again this circle or the projected plane z equal to 0 plane. So, this is z equal to 0 plane. And think of 2 points here, but they are along the same radial line. Okay. So, we have 2 points, point A and point B. So, for the 2 points, what are the various coordinates? So, point A will have radius small r A, and it will have some theta, and z is of course equal to 0, whereas for point B it has a small r B, radius is different, but it has the same theta, and z is of course 0 here again. But what are the E r and E theta associated with the 2 points? So, for both of them, E r is radially outward, it is the same E r, and E theta is in the direction of increasing theta. So, for both the points, E r and E theta are directed in the same direction. And why did it happen? Because for the 2 points we have the same theta. You see, if you measure your theta from the baseline, then theta is same for the 2 points. So, E r and E theta do not change when only the radial coordinate changes, but when theta changes, you go to some other line here with different theta, then you have different E r and E theta, right. So, we can write here E r and E theta change only when the theta coordinate changes. Otherwise, it is constant. Alright, so that was a bit about cylindrical coordinate system. Now, how does a cylindrical element look like in this coordinate system? Can you recall that we had a cuboid element whose faces were parallel to the coordinate plane. So, we had E1 plane, E2 plane and E3 plane. Similarly, here we have to think of a cylindrical element whose faces would have to be parallel to E r plane, E theta plane and E z plane, and then we have to draw the traction components on those faces. So, how will a cylindrical element look like? Let us try to see that now. So, I will again draw the cylinder, and it is a generalized cylinder. So, its radius need not be the same along the axis. all right. Now, any cylindrical element would then look something like this. So, this is one cylindrical element. Let us try to zoom it and take it outside. So, okay, so that is the zoomed cylindrical element. And what can you say about this face? See the top face, what is the normal to this face? That is the z axis. So, therefore, it is the z plane or E z plane. So, this is the positive z plane, and the bottom would then become the negative z plane. What can you say about this face? So, where is the normal to this face? So, you can see that the normal to this face is pointing along negative theta direction, it is pointing in the direction of decreasing theta. So, this is actually negative theta plane, is not it? And what can you say about this curved surface? So, that is the negative E r plane, right. If the cylindrical element is small enough, the curved surface will start to look like a flat surface, and the normal would be along negative E r, is not it? And the outward curved surface has got the normal along positive E r. So, this face is negative r plane. Okay. And when we write down the stress matrix in cylindrical coordinate system, then we have to write the tractions on each of these planes, r plane, theta plane and z plane, and on each of the planes you then have to decompose the tractions in the three basis directions E r, E theta and E z. Okay. So, if we do that here, so let us again draw the cylindrical element. All right. The top face, which is the z plane. So, on that we will have T z, is not it, traction on z plane, and the components, it will have the normal component which will be sigma z z. See, it is the positive z plane. So, sigma z z is going to point in the positive z direction. So, we have sigma z z here. Then we have the component in the radial direction, which is tau r z, right. So, we have tau r z radially outward, and then we have tau theta z in the theta direction. So, from here we could draw this tau theta z. Okay. Then on the theta plane, for example, so the plane that we have here is the negative theta plane. So, all the traction components have to point in the negative basis direction, right. So, here for example, the normal component will be sigma theta theta pointing in the negative theta direction. So, we get sigma theta theta, then we will have sigma or tau z theta, the shear in the z direction. So, that again goes down tau z theta and then tau r theta, right. You see all the components are pointing in the negative direction because it is the negative theta plane. Likewise, for the negative ER plane, all the components have to point in the negative direction, that is the convention. So, here we will have sigma r r, right, and then tau theta r in the negative theta direction. So, that would be something like this, tau theta r, and then we have tau z r, that again goes down, right. So, this is tau z r. So, that is the representation of the stress matrix on a cylindrical element. And just like earlier we were doing the linear momentum balance of a cuboid element. So, we would sum the total force due to traction and due to body force and equate it to rate of change of linear momentum of that cuboid element. Here also we have to find out the net external force on the cylindrical element due to the traction components and the body force and equate it to the rate of change of linear momentum of this element. Okay. So, just like earlier we start with each of the faces. Let us start with the z phase, plus z and minus z plane, and find out the total force due to the traction. Okay. So, on plus z plane, what will be the traction? It is T z, right, and it has 3 components. So, it becomes sigma z z E z plus tau r z E r plus tau theta z E theta, right. So, remember we are now going to integrate over the z plane. Okay. So, the z plane is the top face. And any point on this z plane, what will be the coordinate of that point? So, now we have to think of the dimension for the cylindrical element. So, suppose that along the z it has got delta z, along the radius it is delta r, okay, and the angle this angle is delta theta, and the center of this element, the center of the element somewhere over here within the element, the center has got the coordinate small r, small theta and z. Okay. So, that is the center of the element. So, any point on the top surface here, what will be its coordinate? So, the z coordinate will have to have z plus delta z by 2, is not it? So, z coordinate will be z plus delta z by 2 and that is fixed, but small r and small theta they are going to vary, is not it, and that is how we scan the z plane. So, an arbitrary point will have small r plus zeta comma theta plus eta, is not it, and the third one is z plus delta z by 2. So, we have to evaluate the traction at this particular point and then integrate over the area, and also see what will be the area of a small element here. What is the area going to be? So, suppose this is a very small little area. So, in the radius direction, the side would be d zeta, right. So, in the radial direction, this is going to be d zeta, and in the theta direction, what would that be? The radius times d theta, is not it? And since here eta is the variable of integration, so we are going to vary eta to change theta, so it becomes d eta. So, this one is little r plus zeta into d eta, correct. So, that is the two sides, and then the dA, the area is the product of the two sides, which is simply little r plus zeta into d zeta d eta, right. So, that is the small area on the z plane, all right. So, what is the total force? So, force on the z plane due to traction. So, we have to integrate over the positive z plane the traction plus z, right, dA, which is also the sigma zz Ez plus tau Rz Er plus tau theta z E theta multiplied by the small area, which is here r plus zeta d zeta d eta, is not it, and zeta varies from minus delta r by 2 to delta r by 2, whereas eta varies from minus delta theta by 2 to delta theta by 2, is not it. And likewise, you also have the force on negative z plane, is not it. So, force on negative z plane you are also going to have, which is T minus z dA, and remember what will be T minus z, that is going to be the stress tensor multiplied with minus of E z, because the normal to the minus z plane is minus of E z. So, in terms of the components, all of them get a minus sign then, is not it. So, we simply will have a minus sign outward, and we have the same integration, the integration domain is the same, the negative z plane and positive z plane, the area is the same, right. What is varying is the z coordinate, the z coordinate is z minus delta z by 2, whereas for the positive z plane the z coordinate is z plus delta z by 2, right, otherwise it is all the same. So, this is going to be sigma zz Ez plus tau Rz Er plus tau theta z E theta into little r plus zeta d zeta d eta, correct. What you have to remember is that the traction components as well as the basis vectors have to be evaluated at different points, right. So, in this case, for example, these are evaluated at little r plus zeta comma theta plus eta comma z plus z by 2, is not it? Whereas, the bottom one, that is at little r plus zeta comma theta plus eta comma z minus delta z by 2. So, what should we do now? So, we have to now do the Taylor's expansion, right, because the stress components are varying in the domain, it is varying for different points of the z plane, is not it. So, we will do Taylor's expansion. The force on positive z plane. So, for that we do the Taylor's expansion. So, sigma z z is evaluated at r plus zeta comma theta plus eta comma z plus delta z by 2. So, we have to do its Taylor's expansion and it becomes sigma z z at the center plus the first derivative term, right. So, that is going to be del sigma z z by del r times zeta, is not it, plus del sigma z z by del theta times eta plus del sigma z z by del z times delta z by 2, correct, plus the higher order term. So, that is, you see, it is only the sigma z z part into E z, and E z is fixed for every point. So, E z remains E z, correct. Then we have to do Taylor's expansion of tau r z. So, tau r z is again the same way tau r z at the center of the cylindrical element plus del tau r z over del r times zeta plus del tau r z over del theta times eta plus del tau r z over del z times delta z by 2, correct. And this has to be multiplied with E r. Now, you see E r is also varying from point to point, but we know that E r only changes when theta changes, it does not change if your r coordinate changes or z coordinate changes. So, when you do the Taylor's expansion of E r, that is going to be E r at the center of the element plus del E r by del r, right, del E r by del r. See, it is tricky here, we have to also do the Taylor's expansion of the basis vectors, because they are also changing, it is a bit complicated. For E z we did not have to do, because E z is fixed, times zeta plus del E r by del theta times eta plus del E r by del z times delta z by 2, is not it, into d a. So, here also we have d a and we have got dA even here, and remember that dA is r plus zeta d zeta d eta. And as we figured out that the basis vectors E r and E theta change only due to theta, so these ones are 0. Likewise, we have to also do Taylor's expansion of tau theta z. It is quite complicated. So, plus tau theta z at the center plus del tau theta z by del r into zeta plus del tau theta z by del theta into eta plus del tau theta z by del z into delta z by 2 times E theta. Okay. So, E theta again we have to do Taylor's expansion, and it would become E theta plus del E theta by del theta times eta, is not it, into dA. So, that is only the force on the positive z plane, and you can see that we have to evaluate what is del E r by del theta and what is del E theta by del theta. Okay. So, let us try to evaluate them. So, we again draw our z equal to 0 plane, and here is the origin, and we have 2 points A and B, and each of the points E r is pointing in different direction. And of course, the theta coordinate of A and B are different, and the angle between them would be, let us say, delta theta, right. So, we want to know del E r by del theta. So, del E r by del theta, you apply the fundamental theorem of calculus, and this becomes limit delta theta going to 0, E r for theta plus delta theta minus E r at theta divided by delta theta, is not it? All right, let us join the two vectors here. I mean, let us bring them together so that they pass through a common point. So, we will only parallelly transport them, so that we do not change the direction. So, here is your E r, and that is your old E r, and the angle between them is delta theta. And look at the numerator. Numerator says you do the subtraction. So, when you subtract the two vectors, you will get the third side of the triangle, is not it? So, that is your delta E r. And the magnitude is 1, correct. Let us do a parallel bisection. So, what will be the magnitude of delta E r? You see, this is an isosceles triangle. It is an isosceles triangle. Let me draw it again. So, this angle is delta theta and the sides are 1. So, what will be the magnitude of the base of this triangle? You know, it is not hard to find it out. So, look at this triangle here. If I look at this triangle, the blue triangle, the angle is delta theta by 2 for this triangle, right. This angle is delta theta by 2. So, what will be the height? That is the hypotenuse into sine of delta theta by 2, right. That is a property of right triangles. So, hypotenuse is 1. So, this becomes sine of delta theta by 2, and since it is a perpendicular bisector. So, the total would be 2 times sine of delta theta by 2. So, that is the magnitude of delta E r vector here, 2 times sine of delta theta by 2. And what is the direction? So, that direction, suppose it is some direction E. So, we could write here, this is limit delta theta going to 0, 2 times sine of delta theta by 2 over delta theta, and the direction is some direction E. We can also figure out the direction. You see, in this triangle, what is this angle? So, that angle is simply 90 minus delta theta by 2, is not it? So, the delta E r makes an angle of 90 minus delta theta by 2 from E r, is not it? So, this is your E r, the direction of delta E r makes an angle of 90 minus delta theta by 2 from E r. What happens in the limit when delta theta goes to 0? That angle would become 90 degree, is not it? Because the angle is 90 minus delta theta by 2, and as delta theta goes to 0, it becomes 90 degree. So, can you now see in which direction delta E r is pointing? So, that is going to point in the E theta direction, is not it? So, this E vector here becomes E theta, and what happens to this number 2 sine delta theta by 2 by delta theta. So, you can remember that sin x by x in the limit x going to 0 is simply 1. So, this thing within the circle becomes 1, and the vector E in the limit becomes E theta. So, it is finally E theta. So, we have derived that del E r by del theta is nothing but E theta. You can do similar kind of derivation and show that del E theta by del theta is actually minus of E r. Okay. So, I will not derive it, but you should be able to do it now. It is del E theta by del theta equals minus of E r. Okay. So, we can now plug this in our derivation here. So, this thing here, that is equal to E theta, whereas this thing here, that is minus of E r. Let us think about what is now going to happen. What all are going to survive from this term over here. So, the first term is sigma z z, it is a constant, right. The first term, it is a constant everywhere. So, sigma z z comes out of the integral and then integral of d a. So, that gives you the area of the face, right. What happens to this integral? Del sigma z z by del r is a constant, it comes out of the integral, and then you have zeta d a. What is integral of zeta d a? Zeta was the variation in the r coordinate. So, that gives you the r centroid of the z plane, but because you are measuring zeta from the centroid itself. So, integral of zeta d a is then simply 0, is not it? We have done similar thing earlier also, you can recall. So, this term does not really survive. Similarly, del sigma z z by del theta is a constant, and then you have to do integral of eta dA. And what is the integral of eta dA? That is again 0, because you remember eta varies from minus delta theta by 2 to delta theta by 2. So, this gives you the eta centroid, and since eta is being measured from the centroid itself, that is also 0. And the last one, then we have, you see everything is constant here, it comes out with the integral, and we simply have integral dA. So, you get the area of the face, correct. So, this one we can write here, this is actually equal to sigma z z times the area of the z plane. And what is the area of the z plane? Let us have a look at the z plane. You see what is the area of this z plane? So, along the theta direction, so this line, that is r times delta theta, is not it? So, that line is an arc of a circle, the radius is small r and the angle subtended is delta theta. So, the length of that line is r times delta theta, and this one we know that is delta r. Correct. So, the area is r delta theta. Suppose that delta r and delta theta becomes really small, then this curved thing starts to get straight, is not it? And r delta theta is the line, is the middle line, it is not the outer line or the inner line, it is the middle line which is the average of the two. So, it is like a trapezoid, and r delta theta is the average of those two parallel lines. So, when you do this, you simply get the area, is not it? So, I could write here it is sigma z into area A of the z plane plus del sigma z z over del z times area of the z plane into delta z. So, area of the z plane multiplied by delta z, what does that give you? That is the volume of the cylindrical element, is not it? So, we simply call it delta V. So, this becomes delta V divided by 2, all right. So, now let us look at the second term here. So, the second term has, so if we try to recall, it has the Taylor's expansion of tau r z. So, tau r z plus del tau r z over del r into zeta plus del tau r z over del theta times eta plus del tau r z over del z times delta z by 2 into, you had the Taylor's expansion of E r. So, that was E r at the center plus del E r by del theta, which was E theta. So, this is eta into E theta times d A. Okay, so, that is the integral which we have to work out. Suppose I do first bracket into E r only. So, when you work this out, just as earlier, two of the terms will survive here and rest will be 0, right. So, when I work out this whole thing multiplied by only ER. So, that is going to give me tau RZ into area of the Z face plus del tau RZ over del Z times the volume of the cylindrical element divided by 2. Okay. So, that is only the one multiplication, you have another one. So, we have to now do this whole thing multiplied with the second term. What is that going to be? So, when you do tau RZ times eta E theta dA. So, everything is constant and then you have integral of eta dA, but that is 0, right. For the second term, you will get zeta times eta dA. Let me just write it down. So, the first one is integral and tau RZ comes out, E theta also comes out, and we have eta dA, and we know this is 0. The second one is del tau RZ over del R times E theta and integral of zeta eta dA. It is integral of zeta eta dA. Can you see what is this going to give you without integrating the whole thing? If zeta eta was not there, you simply get the area, but now zeta and eta is also there, which varies. Zeta varies from minus delta r by 2 to delta r by 2. So, zeta is smaller than delta r by 2. Likewise, eta is also smaller than delta theta by 2. So, what you will get finally? It will be of the order of small o of the volume of the cylindrical element. Maybe let us work it out and see what is this really. Okay. So, when you work this out, so this integral you have 1 for zeta, and remember what was dA? dA was little r plus zeta. So, this is little r plus zeta into d zeta, and then integral of eta d eta, right. So, I have completely expanded it, and the zeta goes from minus delta r by 2 to delta r by 2, whereas eta goes from minus delta theta by 2 to delta theta by 2. And what is the integral of eta d eta? It is eta square by 2, and then you evaluate at the upper and lower limit and subtract, but this is simply 0, this is 0, is not it? So, this gives me 0. What other terms are here? So, you also have thing, for example, double integral, and outside you have del tau RZ by del theta into E theta and integral eta square dA. And when you work this out, you will simply get this will be of the order of small o of the volume. So, it is of the smaller order than volume, it goes to 0 faster than the volume of the cylindrical element itself. Okay. And then finally, the last one, that is going to be 0. Why? Because everything is a constant here except for eta. Maybe I should write it down also. So, the last one, it is del tau RZ by del Z into delta Z by 2 into E theta and integral of eta dA, but that we know is 0, is not it? Okay. So, basically there is no contribution from the green multiplications, and what we have is simply the red ones, is not it? Can you now think of what you will get from the last term here? You see, this term is still remaining, and this has got the similar flavor as the middle one, is not it? What is this going to give us then? This would be, so the last one simply gives us tau theta z A z plus del tau theta z over del z into delta v by 2, and this has to be multiplied with E theta, correct, whereas this has to be multiplied with E r. So, what is the total force that we have gotten now? So, force on positive z plane. So, let us summarize it. So, force on positive z plane, that is equal to sigma z z A z plus del sigma z z by del z into delta v by 2 times E z plus tau r z A z plus del tau r z over del z into delta v by 2 times E r, and then the last one plus tau theta z A z plus del tau theta z over del z times delta v by 2 into E theta. So, that is the force on positive z plane. You have to likewise work out the force on the negative z plane. Okay. And can you think of what would be the force on negative z plane? So, look at the expression. So, here is the force on negative z plane. So, you already have a minus sign in the front. Can you see it? So, you have a minus sign in the front here, but then each of the components are evaluated at z minus delta z by 2. So, whenever you do the derivative with respect to z, it will be multiplied with minus delta z by 2. So, you will have one minus coming from minus delta z by 2, and then you have one minus in the front. So, the derivatives with respect to z will become positive then finally, whereas the rest one will be negative, is not it? So, if you allow me to write down, the force on negative z plane would simply be minus sigma z z A z plus del sigma z z over del z times delta v by 2 into E z plus minus tau r z A z plus del tau r z over del z into delta v by 2 times E r, and then you have this term here times E theta. And then we know when we add these two, these are going to cancel, right. And so, the force on positive z and negative z total is simply del sigma z z by del z times E z plus del tau r z by del z times E r plus del tau theta z by del z times E theta, and the whole thing is then multiplied with the volume delta V, and then you also have the small o in the volume. So, you see it was a long derivation, but finally we have the force on plus z and minus z plane. So, likewise we have to work out the force on plus r and minus r plane and force on plus theta and minus theta. You will see they will be even more difficult than this one. Okay. So, we will work that out in the next class. All right. Thank you.